Welcome to SupportDesk. In this walkthrough we are going to troubleshoot a SQL Server deadlock from start to finish. The aim is not just to show the error, but to explain how an application support analyst can reproduce the issue, capture evidence, read the deadlock graph, identify the root cause and recommend a safe fix. The example uses a small order and payment process so the session IDs, SQL statements and results stay consistent all the way through. A SQL deadlock happens when two sessions each hold a lock that the other session needs. Session 57 updates an order row and holds that lock. Session 62 updates a payment row and holds that lock. Session 57 then tries to update the payment row, but Session 62 has it. Session 62 then tries to update the order row, but Session 57 has it. Neither session can continue. SQL Server detects that cycle and chooses one transaction as the victim. The victim is rolled back so the other transaction can complete. In application support, deadlocks often look random to users. A save button fails, a payment allocation rolls back, or a background process reports SQL Server error 1205. The mistake is to treat every deadlock as a general SQL Server fault. A deadlock is usually evidence of a concurrency design problem. It may be caused by inconsistent access order, long transactions, missing indexes, or application logic that does too much work inside a transaction. The support analyst's job is to collect evidence and turn an intermittent complaint into a clear technical explanation. The lab uses a database called SupportDesk_Deadlock Lab. It has two tables, orders and payments. There is one order with order ID 1001 and one payment with payment ID 5001. The order starts as pending and the payment starts as unallocated. This is deliberately simple because the real focus is the locking behavior. In production, the same pattern might involve invoices, care packages, workflow items, claims, tasks or financial postings. To reproduce the issue, open two query windows in SQL Server Management Studio. Session A represents SPID 57. It begins a transaction, updates the orders table, waits 5 seconds, then updates the payments table. Session B represents SPID 62. It does the opposite. It begins a transaction, updates payments first, waits 5 seconds, then updates orders. That reversed object access order is the key. When both sessions run close together, they create a lock cycle. The deadlock victim receives SQL Server error 1205. The message says that transaction process ID 62 was deadlocked on lock resources with another process and has been chosen as the deadlock victim. It also says to rerun the transaction. That wording matters. SQL Server has not crashed. The database is not necessarily corrupt. One transaction was rolled back so the other could complete. Retrying may succeed, but if the same pattern happens repeatedly, retrying is only a workaround. The first triage query checks sys.dm_exec_requests and sys.dm_exec_sessions. During the short window before the victim is killed, you may see session 57 blocked by session 62 and session 62 blocked by session 57. That circular blocking is the deadlock pattern. In real incidents you often miss this live moment because SQL Server resolves the deadlock quickly. That is why extended events is essential. Live DMV queries are useful, but the deadlock XML is the stronger evidence. Most SQL Server installations capture recent deadlocks in the system_health extended events session. The query on this slide reads XML_deadlock_report events from the system health XEL files. Once you have the XML, read it in 4 parts. First, check the victim list. Second, check the process list for SPID, login, hostname, application name and SQL statement. Third, check the resource list to see which table, index or key was involved. Fourth, read the owner and waiter sections. They tell you who held each lock and who was waiting. In this example, SPID 62 is the victim. SPID 57 survives and commits. This does not automatically mean session 62 is the bad query. It means SQL Server chose session 62 as the cheaper or safer transaction to roll back. Both code paths contributed because both accessed the same resources in different orders. A good support note should say that session 62 received the error, session 57 completed, and the common root cause was inconsistent ordering between orders and payments. The root cause is now clear. Session 57 updates orders first and payments second. Session 62 updates payments first and orders second. This is a classic concurrency fault. When two transactions touch the same resources, they should normally touch them in the same order. If they do, one session may wait, but it should not form a cycle. Waiting is inconvenient. A deadlock is worse because it rolls work back. During a real incident, the first priority is to preserve evidence and avoid making the situation worse. Capture the user action, timestamp, database, login and error details. Save the deadlock XML or graph. Check whether the failed action can safely be retried. Do not immediately restart SQL Server or the application pool just because one deadlock occurred. Do not kill sessions unless there is current blocking and an approved business reason. Also avoid changing isolation levels under pressure without testing. That can introduce new behavior elsewhere. The cleanest fix in this example is to make both code paths access resources in the same order. The corrected session B pattern updates orders first and payments second, matching session A. Now if both sessions run together, one may wait for the other to release the order row, but the cycle is broken. This kind of fix usually belongs in stored procedure or application transaction logic. There are other supporting fixes. Keep transactions short. Do not put user prompts, API calls, file writes or avoidable delays between begin tran and commit. Add useful indexes so SQL Server can locate rows quickly and avoid scanning or locking more than it needs. In the demo, an index on payments by order ID can help payment lookups. Indexes do not magically prevent every deadlock, but they can reduce lock duration and reduce the number of resources touched. After the fix, repeat the same test. Run the two sessions close together and check the result. The expected behavior is that one session may briefly wait, then both complete. There should be no new error 1205 for the test timestamp. The final data should show order ID 1001 as paid and payment ID 5001 as authorized. That validation step is important because it proves the fix rather than just explaining it. The repeatable checklist is this. Confirm the user action and timestamp. Capture error 1205 and application logs. Extract the latest deadlock XML from extended events. Identify the victim, the surviving session and the SQL text. Map the lock resources back to tables and indexes. Find the access order conflict, long transaction or missing index. Apply a safe fix, then validate with repeat testing. This is the difference between saying SQL had a deadlock and delivering a useful root cause analysis. For more practical SQL and application support troubleshooting walkthroughs, subscribe to SupportDesk.